Okay, in the introduction chapter of fluid mechanics, we have to deal with the Newton's law of viscosity, which is given as tau is equal to mu into du by dy, where du by dy is called as rate of shear strain. So initially when we have a fluid element in the rectangular shape, and because of the no slip condition, the fluid at the wall has a zero velocity and the velocity will go on increasing. Finally, this velocity is a function of y, as y direction we have shown in a upward direction. So we have a particular velocity distribution here. Because of this, the fluid element which was initially rectangular is deformed like this. So whatever deformation is takes place is measured with the vertical wall is called as the angle phi. This angle phi is called as shear strain. Same thing that we have discussed in torsion also. The rate of shear strain here is the limiting value of the distance change. The distance change will be equal to velocity multiplied by time, and the vertical distance is delta y. In that case, the shear strain is given as the opposite side, which is delta v multiplied by delta t, adjacent is delta y, that is same as angle phi. And this change in velocity is the rate of shear strain, which is given as delta v by delta y. In that case, dv by dy is called as velocity gradient. The unit of velocity gradient is per second. Based on velocity gradient, the Newton has postulated that for a straight and parallel motion of a fluid, the tangential stress, which is force upon area between two adjacent layers, is proportional to the velocity gradient in a direction perpendicular to layers. So shear stress, which is defined as force upon area, is directly proportional to the velocity gradient. So we have a constant of proportionality equal to mu. So we have tau is equal to mu into dv by dy. Here mu is called as the dynamic viscosity, or simply viscosity, or simply called as absolute viscosity. So dv by dy you have to take when there is a velocity profile is given in the function of y. If nothing is given, you can assume the linear velocity profile. If it is a linear velocity profile, then delta v will be same as the change in velocity. So top velocity will be equal to v, bottom velocity will be equal to 0, delta y. So this distance of separation equal to t. In that case, we have t minus this distance is y is equal to 0. So this time we have tau is equal to simply mu into v by t. When we are writing tau is equal to mu into v by t, it means that we have a linear velocity profile. In generalized form, the equation is tau is equal to mu into dv by dy. So this is generalized equation, and if we have a linear profile, then only we can use this equation. Using this Newton's law of viscosity, we are able to calculate the shear stress on a flat plate. But this equation can be applied to number of situations. Based on Newton's law of viscosity, which is given as tau is equal to mu into du by dy, we have a classification of fluid. In generalized form, this equation is given as tau is equal to tau 0 plus mu into du by dy to the power n, where tau 0 is called as yield stress, and the index n will show the variation of how the shear stress will going to change. So if we plot the on x-axis the shear strain, that is the du by dy, on y-axis we'll plot the shear stress, that is tau. So this equation is same as y is equal to a certain constant plus we have mx, and x is same as du by dy. So this is x to the power n equation. As far as the Newtonian fluid is considered, we have value of n equal to 1 and the value of tau 0 equal to 0, because it starts from origin and we have a linear relation. So for Newtonian fluid, we have simply equation is tau is equal to mu into du by dy. Tau 0 is 0 and the value of n equal to 1. Depending upon the value of this value here, we have a dilatant fluid, and the second is pseudoplastic fluid. So in this case, the value of n will be not equal to 1. So this value will be taken as n greater than 1. This value of n is taken as n less than 1. For both this situation, we have tau 0 equal to 0 because the curve is start from origin. No yield stress. Then we have a ideal Bingham fluid. For this one, this is the yield stress, which is equal to tau 0. Once we have overcome the tau 0, then we have a linear behavior. So for this one, we have equation is tau is equal to tau 0 plus mu times du by dy, power is 1, because we have a linear distribution shift. So there are number of fluids we have to introduce here based on the classification of shear strain. We have a Newtonian fluid, other are called as non-Newtonian fluid. In the non-Newtonian fluid, we have a dilatant fluid, pseudoplastic fluid, and the ideal Bianchum fluid. Depending upon the shear stress and the time, there is a change in the viscosity, so that we can give as rheopatic fluid, then we have thixotropic fluid, and we have common fluids. So as far as the common fluid is considered, the shear stress will not change with respect to time. As far as the rheopatic fluid is considered here, the shear stress will go on increasing with respect to time. So for this one, we have d tau by dt, that is the shear stress with respect to time will going to increase. This is a positive slope. And for this one, we have a negative slope. So we have d tau by dt is negative value. So these are the further classification of fluids based on Newton's law of viscosity. Now here mu, which is defined as tau divided by du by dy, as unit of Pascal second, and in SI unit, its unit is kg per meter per second. So it has a dimension of m, l minus 1, t minus 1. So this one is a physical property which exists in a fluid, by virtue of which it offers resistance to the motion of the fluid. Similar to the mu, we have another property equal to nu, that is given as mu divided by rho. By substitution, if we put for mu equal to m l minus 1 t minus 1 and rho equal to kg per meter cube, in that case we will get meter square per second. This one is called as kinematic viscosity, and this one is called as dynamic viscosity. So another unit of this one is Stoke. 1 Stoke is equal to 1 cm square per second, which is equal to 10 to the power minus 4 meter square per second. And the smallest unit is 1 centistoke, which is 10 to the power minus 6 meter square per second. Similar to this, we have 1 poise equal to 0.1 Pascal second. Similarly, we have 1 centipoise equal to 10 to the power minus 3 Pascal second. So this smallest unit of 1 centistoke and 1 centipoise is assigned to the water, and with reference to the water, another viscosity is measured. Both the viscosity here, that is a mu, is a physical property, and that very much can be defined on. In the case of liquids, it is defined on the basis of cohesive forces, and we know here the cohesive forces will break down at a higher temperature. So as the temperature will increase in the case of liquid, the cohesive forces will break down and the molecules are free to move. It means that the viscosity will going to decrease. So here we have a graph of viscosity of water versus temperature on y-axis. Y1 axis and y2 axis is viscosity of air. What we observed here is that at 0 degrees Celsius, the viscosity equal to 180. Then as the temperature will go on increasing, the viscosity will drop here. At 100 degrees Celsius, it will very close to around 25 to 30. That is maybe here 10 to the power minus 5. So that is 20 into 10 to the power minus 5 Pascal second. So for liquids, the viscosity is inversely proportional to temperature. Whereas the viscosity in the case of gases is defined on the basis of intermolecular momentum, because the cohesive forces are very weak, and therefore we cannot define the viscosity on the basis of cohesive forces, rather it is defined on the basis of intermolecular momentum, which is clearly is a function of mass and velocity. Now in the case of gases, as the temperature will increase, the velocity will increase. As the velocity will increase, the momentum will increase. As the momentum will increase, you will get more resistance in the gases, and what we claim here is that the viscosity will increase. Indirectly, the viscosity is directly proportional to temperature. So here we will find here the graph of air, and at 0 degree Celsius the viscosity is very low, and then as the temperature will go on increasing, the viscosity also go on increasing. So both are exactly opposite. In the case of liquid, mu is inversely proportional to T, and in the case of gases, it is directly proportional to T. If the fluid flow is taking place between the flat plate, it is called as Cotti flow, and in particularly the Cotti flow, the top plate is moving and the bottom plate is fixed. So, and this fluid is filled with a viscosity equal to mu. In that case, we can very well apply the Newton's law of viscosity, which is same as tau is equal to mu into dV by dy, which is same as mu into delta V by delta y. If we assume here the linear velocity profile, then we have the tau is equal to mu into v, that is the velocity of the top plate by the distance of separation of the two plate equal to a. The second type of flow is a possible flow. This type of flow normally occurs in the case of circular pipe. When a fluid is moving in a circular pipe, we will get a velocity profile is a parabolic profile. Velocity at the center is maximum, and due to no slip condition here, the velocity of the wall is 0. So the fluid velocity is also equal to 0. In that case, we have at any radius r here. The distance in this case is always measured from the fixed plate, that equal to y. So this capital R will be equal to y plus r. In that case, we can write y is equal to capital R minus small r. Capital R is the radius of the pipe, small r is any radius where we are interested to know the shear stress. So if I differentiate here y, if I partial differentiate here, I will get dy is equal to 0 minus dr. So in that case, this law, that is tau is equal to mu times dv, and we can replace here dy as minus of dr. So in the case of circular pipe, this law become minus of mu into dv divided by dr, where v is the velocity at the distance equal to r. So this is the difference between the Corti and the possible flow. Suppose we are given the velocity distribution between the three plate. In between the top plate and intermediate plate, we have top plate is moving with a velocity equal to 3 meter per second. Bottom plate is moving with a velocity equal to 2 meter per second. These two plates are separated by distance equal to 0.02 meter. Intermediate plate and the bottom plate is here fixed. So the velocity on the bottom plate will be 0, and we have viscosity equal to mu n and viscosity equal to mu 2. Suppose we are interested to know what is the shear stress on the top plate and what is the shear stress on the intermediate plate, that you can very well calculate. So for this purpose, we will consider here this velocity difference. So we have tau 1 is equal to mu 1. Corresponding velocity difference is 3 minus 2, and corresponding distance change equal to 0.02. If you want to calculate tau 2, then you have to consider these two plates. So this velocity equal to 2, bottom velocity equal to 0, and the distance of separation equal to 0.02. In this fashion, we can calculate tau 1 and tau 2. This time we have a shaft is rotating with a speed equal to n, and this one is a bearing. The length of bearing is equal to L, and the internal diameter equal to d, and there is a radial clearance equal to t. So first look is that the Newton's law cannot be applied here because this one is a circular element, but that is not the situation here. In that case, suppose we do the development of the shaft and the development bearing. In that case, we'll get the flat plate. So one flat plate will be shown as a circumference length equal to 2 pi and the length of bearing equal to L, and this plate here are separated by distance equal to t. So this model is same as the two flat plate moving with a velocity equal to v, and the bottom is bearing here, which one is stationary, that is the bearing casing is stationary. So we can very well apply the Newton's law of viscosity here. Each and every particle of the shaft here, that is on the periphery, which comes in contact with the oil, is at a uniform distance equal to d by 2. So linear velocity for all these points is remains same, and that equal to v, which is equal to omega multiplied by r. So at this stage, we can apply the Newton's law of viscosity, assuming that we have a linear distribution. So we have tau is equal to mu into v by t. Once we know the tau, then we'll multiply this area, that is the weighted area here, which is equal to circumference multiplied by length, and we can calculate here how much force is required to overcome the friction, or we can find out here how much torque is required to overcome the given friction. This one is the case of journal bearing, can also be solved with the help of Newton's law of viscosity. Here we have a two parallel disc, and there is a relative motion between the two discs. One is called as driver, other is called as driven, and they is separated by a very small gap equal to t, and there is a casing here. So when the driver is moving, with respect to the driver speed, some relative speed is possible here. Suppose it is rotating with a speed equal to n1. Since we don't have a positive drive here, the power is transmitted by means of fluid. This speed will be equal to n2. So if we hold the n2, in that case the fluid will be get sheared by the difference of the velocity equal to n1 minus n2. So that is the relative speed. Now this concept here again can be solved, that how much power will be wasted in overcoming the friction, or how much torque is required to overcome the friction. So if you see the front view of this one, you will get one plate. second plate will be just overlap here. But what problem here in this case is that for the as the distance from the axis will change, the linear velocity for all these points will also change. Angular velocity will remain same, but the linear velocity will change. So whenever the linear velocity will change, we'll take the concept of integration. For this purpose, we'll consider here one elemental ring of radius equal to r, thickness equal to dr. This same theory we have used in the clutches, that is for uniform wear theory and for uniform pressure theory. So we have dA is equal to 2 pi r dr, and the velocity at this ring will be equal to omega into r. So for this ring, we'll first calculate the elemental shear stress. By definition and assuming linear velocity profile, we'll get mu into v by t. Replace v by t as omega into r. What we get is d tau is equal to mu into omega r divided by t. Now once we know the shear stress, then we can calculate the shear force multiplying by dA, and then we'll again multiply it by r to calculate the total torque required to overcome the friction. So substitute all this value, integrate it. Since we have the limit is from 0 to r, substitute the limit, solve the integral. Finally we'll get the total torque required to overcome the friction between the two parallel discs is equal to 2 pi omega mu divided by t r to the power 4 divided by 4. Remember here, this value of n1 you have to calculate as n1 minus n2. That is the rotational speed, and then you can convert into angular speed. Another type of problem will be based on the Newton's law of viscosity. In that case, we have a block, and in between the block and the surface here, we are maintaining here a thin layer of fluid. So this one become a problem of wet friction. So if there is no layer, it is a case of dry friction, and the problem of dry friction you have to solve by using the Coulomb friction, that is the value of mu. But if the layer is maintained here, in that case we can still apply the Newton's law of viscosity. For this one, you have to first find out which force is responsible for motion. So whatever the weight component is there, you have to resolve the weight component into two parts. One is parallel to the plane, which is mg sin theta. One is perpendicular to the plane, which is mg cos theta. Now this force here, mg sin theta, is an unbalanced force. Because of this unbalanced force, the block will start moving in a downward direction. As the block will start moving in a downward direction, the film form here will be get sheared off, having a distance of separation equal to t. So it's a very small gap. So the fluid will be sheared off here, assuming the linear velocity profile. Because the gap is very small, we have this force, which one is mg sin theta, is responsible for overcoming the shear stress. So we have mg sin theta is equal to shear force, that is tau multiplied by area. Now here tau we can replace by using the Newton's law of viscosity, which is mu into v by t, and now you can find out here the unknown value, whatever is required for you. So this time value of mu is required, that can be comfortably solved by balancing the sigma fx. Along the x direction you have to balance this force. This force is mg cos theta, will develop the normal reaction. This normal reaction is useful in the calculation of dry friction, and n has no role in the case of wet friction. Second idea is about the surface energy or the surface tension force, which is denoted as sigma and is basically force per running meter length, that is F by L. So unit is Newton per meter. Now this quantity Newton per meter we can very well write as Newton meter divided by meter square. Newton meter is nothing but energy, and this one is called as density. So sigma is also called as the surface tension force coefficient, or is called as energy density. What is observed here is that, suppose I show here molecular levels, all molecules here on the top surface, then we have second layer of molecule, third layer and fourth layer. If you see this molecule, then this molecule is surrounded by the same molecules here, so it is pulled up equally in all direction. But if you see the top molecule here, in that case this molecule is pulled in a downward direction, and we have another molecule here of different material. In that case this film will be get stretched, and when the film is get stretched, that is come in the tension because of this second layer of molecules. That is called as the surface tension. So that is why the term sigma is introduced, to account for the both, that is the cohesion as well as adhesion. Cohesion is the force of attraction between the two similar molecules, and the adhesion is the force of attraction between the two dissimilar molecules. Depending upon the cohesion is a strong or adhesion is strong, any surface will get wet. Suppose we have the angle is less than 90. In that case, in the case of mercury, if you drop a mercury on the ground, you will find here that it will form a droplet of water. So there is a strong force of cohesion than the adhesion. But if the water is dropped, in that case the surface will get wet. So if the water is dropped here, in that case what we observed here is that the water will spread away. It means that it has a more contact of area. So based on this area, we can say that the surface is wet or the surface is non-wet. It is entirely dependent on the contact angle theta. For contact angle theta, in the case of mercury is taken as approximately 130 degree, and the contact angle for distilled water is taken as 0 degree. It means that if it is distilled water, then it will spread here on the flat surface. Solve the problem of surface tension force in the case of raindrop, in the case of bubble, and in the case of spherical bubble. You have to remember here that delta P is the excess pressure, which is given by sigma divided by R. We have delta P is equal to sigma by R for cylindrical jet. Cylindrical jet is this shape. That is the cylindrical jet. We have delta P equal to 2 sigma divided by R in the case of raindrop or in the case of bubble. Bubble and the raindrop, they are identical situation. In the case of raindrop, we have a spherical drop of water is surrounded by air. So in this case, the film is stretched on one side only. In the case of bubble, we have air inside and we have liquid outside. So this time the film is stretched on one side only. Whereas we have delta P equal to 4 times of sigma divided by R in the case of soap bubble. The soap bubble is a very thin ring of soap film. So this film is a soap film. Inside is air, outside is air. So this time the film is stretched on both sides, and the thickness of the film is very small. So this model is almost double the model of raindrop. So these are the value of delta P. So we can very well find out the equation using this. Suppose we have given here this cylinder here. In that case we have length equal to L. So suppose they will ask you how much force is required. So you have to take this force along this periphery and one force along this periphery. So total force here will be equal to sigma into L. On this side also we have sigma into L. So total force required here in the case of needle. So this one is an example of needle. To lift the needle from the surface, we require a force F, which is equal to 2 times sigma L. This time we have a annular ring given here. You can imagine it's a bangle. So this surface is get wet here, as well as the outside surface will also wet here. In that case we have the total force required from the inside here, that is this force, will be equal to sigma multiplied by pi multiplied by do, and this force required on the outer periphery will be sigma multiplied by pi multiplied by do. So the total force required in this case will be equal to the force required for inner ring, that is sigma into pi into di, and for outer surface is sigma into pi into do. So total force required will be sigma into pi into do plus di. In the case of surface tension, we will also observe here is that we have a capillary rise if a very small diameter tube is immersed in a liquid. Now right now we discuss here except mercury. In that case we have a rise of liquid equal to H, and we have a meniscus is formed here. This meniscus makes an angle equal to theta. So this one is the direction of surface tension force. This surface tension force we can resolve into two components. One is sigma cos theta and one is sigma sin theta. So this surface is get wet here. So I will show here this surface, and the total surface tension force is acting in a upward direction. This total surface tension force will be equal to the circumference multiplied by vertical component. So we have vertical component is sigma into cos theta, and the circumference is 2 times pi multiplied by r. Because of this force, the liquid will rise here. So you have to calculate here the weight of this liquid. Weight of the liquid will be given as rho multiplied by g multiplied by volume, which is equal to the cross section area pi r square multiplied by h. So this time we are able to calculate the capillary rise h. One of the r will be get cancelled. one of the pi will get cancelled. We left here 2 times of sigma multiplied by cos theta divided by rho g divided by r. Now clearly here h is inversely proportional to r. It means that we have a smaller radius, then the capillary rise will be higher. At the same time, h is also function of theta. This value of theta will you have to take equal to 0 for water, that is distilled water. And this value of theta is equal to 130 in the case of mercury. In that case, we will observe here that the cos of 130 is negative. And since the cos of 130 is negative, we have h will be negative value. In that case, it is called as the capillary depression. So capillary depression is only possible in the case of mercury, clearly indicating that we have a very strong force of adhesion. So it means that if theta is greater than 90, then adhesion force is greater than cohesion. In that case, if we have a capillary, then the meniscus will form like this, and this one is a level in the tank of mercury. So this level is drop here by height equal to h, and when we have theta is less than 90, in that case we have cohesion is strong compared to adhesion. In that case we will get this type of liquid. Here the cohesion is strong as compared to adhesion. Another useful property is the bulk modulus. Bulk modulus is simply given as dP divided by dV by V, which one is volumetric strain. And since here we know that mass is given as density into volume, and since the mass is remain constant, so partial derivative of dm will be equal to 0, and the partial derivative on the right hand side is rho into dV plus V into d rho must equal to 0. In that case, if we fall here for dV by V, I will get minus d rho by rho. So basic definition is based on volumetric strain, and because of this minus sign and this minus, it becomes positive. It clearly indicates that the pressure as the pressure will increase, the volume will decrease. Now there is an inverse relation, and therefore to get the value of beta positive, we introduce here negative sign. But when the pressure is increased, the density also increases, so there is always a positive sign here. So that is why we introduce here negative sign to satisfy the relation that the pressure increases, then the volume will going to decrease. Same thing we have shown here also. Now remember here the bulk modulus in the case of water is 2.1. In the case of steel it is equal to 160. Bulk modulus for steel that we have already done in the strength of material, E is equal to beta, that is K into 1 plus 2 times of mu, which is almost equal to, this value is equal to 80. So beta of steel is 80 times the bulk modulus of water. The video you are watching is from the app, which is the More Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.